So the director of Privacy International said, the defense of privacy will be the savior of the future. But why is privacy so important? It's a fundamental human right. The Universal Declaration of Human Rights says no one shall be subjected to arbitrary interference with their privacy, family, home, or correspondence. And it's necessary for democracy. Without privacy, you end up with mass surveillance, monitoring and crushing of dissent, voter manipulation from profiling, and swinging of elections. Most of our lives these days are online, so if you want to protect privacy, you need to protect online privacy. So let's have a look at what happens right now if you visit a website. First of all, your browser will do a DNS lookup, which leaks the site you're looking up to wherever your DNS server is. Then you'll open a TLS connection to the server. This involves trusting about 140 certificate authorities in your browser. If any one of those are compromised, it's game over. You then load arbitrary code from this server, whatever it sends you. And that code then typically will start loading some third-party code from other domains, which will repeat that dance of the first 3 steps. And then maybe you might log into the site. You might have a username and a password you send in. And probably if you're going to log in, you're going to start sending some kind of personal data. It could be documents or whatever. And if it's a social site, something like Facebook or Twitter, then there'll be a feed which you see of stuff, and that feed will be curated by an AI whose interests are not aligned with yours, but with advertisers. And the end result there is subverted democracy and compromised consensus. So could a better design fix these problems? I wouldn't ask that if I didn't think the answer was yes. But let's talk about the requirements. So ideally, we want to protect against third-party and, if possible, first-party surveillance. We want to remove the incentives, the structural incentives that resulted in surveillance capitalism being the dominant business model on the web. And in doing so, we want to return data and identity ownership to users. You should be able to take your data transparently between hosts or between apps. It should work in existing browsers, and it should work offline. And critically, like, you can have super amazing privacy, but if it's not usable, no one's going to use it. So it has to be easy, it has to be convenient. So these were the requirements we had in mind when we started working on Peergos. So Peergos, it's a global end-to-end encrypted file system. You have fine-grained access control, so you can grant different kinds of access to individual files or entire subtrees, entire directories. Everything is signed and content addressed, which makes it host independent, so it doesn't matter where your server is. There's automatic host migration, so you can move to a different server and all your existing links will continue to work. So far it's just an app. The next thing is a sandbox. This is a sandbox for running sites or apps, like third-party stuff. And of course the whole thing is built on self-sovereign identity. So with any kind of something that's trying to build a web, you've got to think about structural incentives. So what are the emergent outcomes from the way it's designed? And one of those will be who's going to run it. So some people will want to self-host it. A lot of the web is like that, but a lot of it's not. So you're going to need storage providers. And the fact is most people are not going to run their own server. They either can't or they won't. And so what we wanted was no privacy improvement from self-hosting. So some protocols don't worry about encryption. They say, oh, if you want privacy, just self-host. You've ruled out 99% of people. So if you want everyone to have privacy, it has to be built in. So that means you need to have encryption and trustless servers. So this is a standard peer-to-peer architecture. Every Peergos instance has an embedded IPFS instance. They all talk over libp2p. They do RPC calls to each other using just standard HTTP requests, but HTTP over libp2p. And yeah, so the communication it's all TLS or noise, but critically there are no certificate authorities or no DNS requirement. The servers are trustless. That's true of most stuff here, basically because it's content address data and updates are signed. The additional layer we have is public key infrastructure. This is just for human readable names. And because of these properties, you end up with location-independent addressing, which is how you get your server freedom. So compare that with the current web. When you do the DNS lookup, it's location-based addressing. So you're talking to a particular server, and that server gives you whatever they want to give you. So the identity, the PKI, it's a mapping from your username to two public keys: your identity public key and your home server public key or peer ID. And this is just it's an append-only Merkle log of signed name claims. It's similar to certificate transparency logs, except we use it as a source of truth, not some retrospective check that you can do. And the actual data structure we use is a compressed hash array mapped prefix trie. You'll see a lot more about that because we use that in a bunch of other places as well. It's a fun data structure. What kind of properties does this identity have? Well, it's host independent. We've mentioned that. It's tofu, so if you trust on first use someone's keys that you get from the PKI, but you can also verify in person via QR code or numbers or whatever. And that uses the same algorithm that Signal uses. When you upload a file to Peergos, the raw file is first split into 5 megabyte chunks. Each of those chunks is independently encrypted and then split into 5 1 megabyte blocks. And those are then put into IPFS along with the encrypted metadata. The way this looks at the block level in IPFS, you have the blocks are put into a champ, so you have the internal champ nodes, and then the encrypted metadata is called cryptree, so that's the cryptree node, and that can link to your up to 5 blocks. So let's talk a little bit more about this champ thing. So compressed hash array mapped prefix trie, it's a key value store. It's independent of insertion order, unlike a B tree, and it's balanced. In the Peergos file system, the champ keys, the lookup keys, they're just random 32 bytes, and the values, as you saw, are cryptree nodes. In terms of metadata privacy, your host can't see file sizes. That's basically because the different chunks of a file in the champ are not linkable by the server. And as well as that, even within a chunk, we pad to a multiple of 4K. Your host can't see whether a particular chunk is part of a file or a directory. It's the same format. It can't see the file or folder names or even the size of the folder names, again due to padding. It can't see the folder topology. So there's really not much your home server can see. We also protect your social graph and also who or even how many have access to a particular file or blob. The last one you basically get for free from capability-based access control. So this is what the cryptree format actually looks like. There's 3 main sections, and this thing at the top called BATS. We'll talk more about those. BAT stands for Block Access Token. It's nothing to do with blockchain. And each of those sections is padded to a multiple of 64 or 16 or 4K. And the first 2 you need, there's a different key to decrypt each of these. So the way this is the cryptree structure that we use. So each file or directory has 2 symmetric keys, a base key and a parent key, or for a file, a parent key and a data key. And the idea is if you have one of these symmetric keys, you can follow these links you can decrypt stuff in the cryptography nodes to follow these links around this tree. So if you have the base key for a directory, you can then decrypt the capabilities for the children and retrieve all the children and so forth recursively until you get down to the files. If you, for example, only have the parent key of the file, then you can follow those backlinks to get that allows you to decrypt the metadata of all the parent directories, and that's how we get a well-defined path. The write crypt tree is a bit simpler. There's just one key, one symmetric key for each thing, and if you have that symmetric key, then you can derive the signing key pair, which is used to do updates to that thing. Now, unless you've granted write access to something, then your entire file system is in a single signing key pair space. So all those key pairs are the same unless you start granting write access. So I've mentioned capabilities, so what do we actually mean? So the capability it's pure information. It's not identity based. So the idea is if you have a capability, then you can do a thing. And there's different kinds of capabilities. Because they're pure information, you can just share them via whatever means you like. You can put them in secret links, etc. The three kinds of capabilities we have: mirror, read, and write. Read and write we've just explained. They're fairly obvious. Mirror is basically the ability to retrieve the ciphertext. So if you want to, for example, run or run another server that mirrors all your data from your home server, you have to give it a mirror capability to your file system. And so the mirror capability is made up of four things. There's the owner and a writer. Those are both public keys. There's the map key, which is the lookup key into the champ, so that's just 32 bytes. And the bat, which we still don't know what that is, but we'll talk about that in a second. So the bat is the bit that actually is enforcing the mirror capability access. So let's have a look at what actually happens if I have a capability and I want to retrieve it. So you use the PKI locally to look up the owner's host peer ID. So that's from the owner part of the mirror cap. So you look up from the owner, you find their peer ID, and then you do a peer-to-peer HTTP request to their host to get the mutable pointer for the writer. The writer was the second public key in the mirror bit. And once you've got that, you verify the signature, and there's a so the mutable pointers, they're assigned pair of hashes, the previous root and the current root, and a monotonic sequence number as well. And then once you've got that, you get the root hash out of that, and you do another peer-to-peer HTTP request, which is a champ get. This is just a convenient way to ask the server to do the champ lookup for the thing that you have and return all the blocks. So it just returns the blocks on the lookup path. And then once you've got the response to that, you repeat the champ lookup locally so that they can't trick you with anything. And you've then got the metadata node, so you then use the read key if it's a read capability, and decrypt the metadata. If it's a file, then you might have some blocks that you need to retrieve as well, so they'll have their own links which you need to go and get using the bats which are in the cryptography node which you've just got. You concatenate the blocks and decrypt, and there you go. So you've got the first chunk of the file. So now, what about the rest of the file? Well, you've got to repeat the last few steps with the next chunk of the file will have a different map key and also a different bat. Now the map keys, these are calculated by basically the hash, the SHA-256, of a thing called the stream secret, which is it's just 32 bytes stored in the encrypted metadata of the first chunk of the file, plus the current map key. So you iteratively figure out the later map key to look up in the champ. So this is the thing that protects the linkability of different chunks in the same champ from your server, because the server doesn't know the stream secret, so he can't figure out subsequent chunks. And the same hashing thing is used for the bats as well. So you can see that here. So a bat is the same thing as SHA-2 physics of the stream secret and the bat. So we didn't always do it this way. So originally, the subsequent chunk labels were just random, and basically it was a linked list. And that worked, but if you wanted to seek ahead in a large file, you would have to get the metadata, do a champ lookup for every single prior chunk, which is obviously dumb and slow. So we stopped doing that and used this scheme. So in this scheme, if you want to seek ahead, all you need to do is a bunch of local hashing, which is very fast, and then a single network call to do a champ get to retrieve the encrypted metadata and then get the blocks. So it's O of 1 in network I/O. So now let's see a demo of that. Is this working? Cool. Yeah. All right, so this is Peergos. Let's find. So this is Intel, I think. Yes. I think I have the sound on, but we'll see. Cool, I love it when demos work. Well, that's exciting. Let's try a different one. Well, I can't, this is a small movie, I can't do seeking in this. I wonder if the internet's... Yeah, but it hasn't even started playing yet. Love it. All right, I'm just going to...
Is your browser using any browser-based libp2p, or is it going through an HTTP gateway?
Neither. So this happens through the Peergos server you're talking to. So if you do a champ get to someone else's that's not on the same server you're talking to, that will go. The server will send that over a peer-to-peer stream. Demo gods are not happening today. Wonderful. What about this one? All right, well, first demo failed. Interesting. All right, let's go back to the slides. I'll try that again in a second. So block access tokens, what are they? The basic premise is, yes, you can encrypt your data, but even ciphertext you shouldn't make public. So don't just publish it on the DHT. BATs give us a post-quantum ciphertext access control mechanism. There are 2 BATs per block. There's a unique BAT for the block and a user-wide one called a mirror BAT. As the name suggests, the mirror BAT is the one you give to another server if you want it to mirror your entire space, your entire file system. The actual signatures are S3v4 signatures, which under the hood is basically HMAC SHA-256. So this works out to be 89 bytes encoded. And so we had to modify BitSwap to do this. So BitSwap, our version of BitSwap, accepts this additional auth token, auth string, is paired or optionally paired with every hash that you ask for. And then the recipient can then enforce that. The signature is tied to the requesting peer ID, so you can just broadcast these signatures, and no one else can use them, and of course to the time as well. So the unique bat for each block is called the inline bat. We basically have two kinds of blocks. We have CBOR blocks, DAG CBOR blocks, and raw blocks. For CBOR, it's easy. Most of them are, the root object is a map, so we just put a new key in the map called bats, and that has the two bats in there. Raw blocks are a little bit more involved because there isn't any structure there except at the start of the block, basically. So what we came up with there was there's this magic 8-byte prefix, and if that's there, then the next 77 bytes are just a CBOR list of the two bats, and then the actual data of the block. And so these bats, they're 32 bytes each. So this is about a 60-byte overhead. But given we're already rounding up blocks, at least data blocks to 4K, that's not a significant overhead. So what about login? So you have your username and your password and a public salt. This goes into script. Two things come out of script. You get your login key pair and a symmetric key. The login key pair isn't used for anything except authing with your home server to retrieve your encrypted entry data, which you then decrypt with the other symmetric key. And the result of that is your identity key pair, your social key pair, and your root capability. We don't think humans should create passwords most of the time. So we generate your password, 7 words from a 2,000-word list. Generated passwords have 77 bits of entropy. A GPU can calculate about 1 million script hashes per second. This is going to be a conservative estimate because we use stronger parameters than this measurement uses. But with that, one GPU would take 5 billion years to crack one of these passwords. And even if you had 1 million GPUs, which some people do these days, it would still take 5,000 years. You can do a plot of the cost to break a password, brute force a password in 10 years. And this is ignoring the electricity cost. This is just the cost of buying the GPUs. So don't use 2, 3, or 4 words. 5 you might be okay. We've gone with 7, and you can see the NSA budget there. What I haven't discussed so far is how does the social side work. Basically, you have an encryption key pair, and you have an encrypted inbox which you can send follow requests to. These are blinded, so the recipient server doesn't see who's connecting with who. And if the recipient accepts it, then you basically get a secure channel which you can then share other stuff on. So far, it's just an app. If you want to do third-party stuff, then we need a sandbox. The goal for here, as I mentioned at the beginning, was to run untrusted code over private data, such that an app can't exfiltrate data. An app can't read anything it's not been granted access to. And yeah, it needs to work in existing browsers without add-ons and offline. And so one of these apps ends up with a simple REST API. There isn't a server. Basically, the REST API is handled by a service worker. And so an application is, it's just a folder of HTML5. Because it's just like any other folder in Peergos, the author can control the visibility. It could be private, it could be public, you could share it with people. And there are basic permissions an app can request. For example, you can register for certain file types if you want to, like a document editor or something. And yeah, publishing is easy, drag and drop. And an app without any permissions is basically just a private website. So yeah, you've got this built-in kind of private website thing. There's a kind of special browser app which renders these folders of HTML. in such a way that it isolates different folders. You can have internal links, external links, and it'll render markdown pages and things like that. How does it actually work? We use a random subdomain. The hash in this case is the hash of the human-readable Peergos path that the app is being served from, because those are globally unique, and that means all the apps are isolated from each other. And we use CSP and co-app headers to isolate this, so the subdomain ends up in a different operating system process, and the actual server serves up the same static assets for all subdomains, and all those assets do are set up the service worker, which then loads the app. And from that point on, it communicates with the main Peergos context, the trusted one, via post messages. So the trusted Peergos context is the bit that enforces the permissions and retrieves the data and does all that stuff. What can an app do? So you can edit files, spreadsheets, image editor. I mean, it's the web. You can do anything. You can have a media player, multiplayer games. Starts to get interesting with chat. There's a chat API that apps can use. Essentially, you can create conversations and send messages to your friends in Peergos. And the chat protocol itself, under the hood, uses a CRDT-based chat implementation, which is basically just a file in Peergos, an append-only file of messages for each member of the chat. Or you can play Doom. Right, let's see if this demo goes any better this time. Right, so let's see, what have we got? So this is a docs folder. It worked, hooray. So that's a document editor. It's a Microsoft Office document editor. There's also ODTs, open document type, or whatever it is. Let's see, a spreadsheet. So this is an Excel spreadsheet. So we haven't written these apps ourselves. These are just standard web apps, open source web apps that we've done some minor changes to port to use Peergos. Where are we? There's a block-based note editor in here. Let's edit it. So this is, you can do block-based stuff, inline images, LaTeX, lists, code, tables, mermaid diagrams, stuff like that. Add stuff. Where's it gone? There we go. La-di-da. So that's the Notes app. I'm going to try the video demo again and see if it works this time. It's playing. Wonderful. Don't know what changed. So we have sound, hopefully. That might just be my laptop, but okay, anyway. So this is Syntel playing. You can see how much it's buffered down there, not very much. We can seek ahead. This is not a huge file, but it's big enough to demonstrate. It's 120 meg. So let's jump over here. It's about a second to seek ahead. Now you might be asking that seeking thing involves hashing to go forward. How do you go backward? We could optimize this more, but at the moment we just go back to the start and hash forward. That's fast enough for use cases. So I mean, well, you can see for yourself. So there we go. Cool stuff. What else can I share with you? So I mean, yeah, the viewing a folder as a website. So you can see this has just got an image and an index HTML. We can just open that and it renders in the sandbox there. Now this, oh, there's another one, there's a calendar app, I haven't shown you that. So the model for this is, it uses standard iCal, and each event is just a file in Peergos, so you get your built-in access control, you can share individual events. You can have multiple calendars, each calendar is a folder, so you can use the folder sharing to share access to calendars. And whatever, you can share it, download it, the usual stuff.
Are you up for questions?
Yeah. So yeah, so that's the end of the demo. Right. So then just a little bit more. So the one important app is social media. So we think public social media is bad for society, at least public by default, because it allows micro-targeted political profiling and it's open to abuse, but also because public is a little bit like infinity. Most people don't understand it and the consequences. So like if you'd asked someone 10 years ago if they thought that all the photos they posted online were going to be fed into some AI and stolen, they probably wouldn't have thought of that. But on the other hand, normal in-person conversations are good. That's how we reach consensus. So Peergos social media is modeled on in-person conversations. So it's all end-to-end encrypted. A post is, again, just a file under the hood. You can post images or text or whatever. And if the original poster decides the audience who sees a post, and they also decide who can comment on it, and the comments flow sort of friend to friend in an end-to-end encrypted way. So that, again, the server sees nothing. Without privacy, there can be no democracy. So yeah, go have some fun, self-host, or sign up on peergos.net, write some apps, protect yourself in democracy.